Okay, welcome everyone to our Earth Emergency Cluster lecture by Professor Tim Palmer. It's a real pleasure to have him here. Tim Palmer is Royal Society Research Professor in the Physics Department and Senior Fellow at the Oxford Martin School. He's very much interested in the dynamics and predictability of climate and weather and its extreme events. He studied math and physics in Bristol and then actually was at Wolfson for his DPhil in general relativity. So how come the detour to climate? Well, like many things in our life, a chance encounter, in this case with Professor Hyde, got him interested in climate. And from there on, yeah, we now have one of the world leading researcher in this field here. Tonight, he went on to work at the Met Office. He was involved in the first 5 IPCC assessment reports. He was co-chair of the International Scientific Steering Group of the World Climate Research Program, and the list of awards is long, from a Fellow of the Royal Society to a CBE and an international member of the US National Academy of Sciences. With that, I would like to invite Tim for his lecture, and I'm really very much looking forward to it. Thank you very much.
Thank you very much. Thank you for coming out on this wet evening. So I guess everybody knows CERN, the High Energy Physics Center in Geneva, and I guess it's a little more than a decade ago that they discovered the Higgs boson. Now, people may not care anything about the Higgs boson, but the only thing you need to know is that, apart from the fact that particle physicists think it's very important, it's the sort of thing that could only have been done at an internationally funded institute like CERN. Discovering the Higgs with the so-called Large Hadron Collider was really beyond the budget of individual countries, maybe the US, but they had sort of decided they didn't want to do that sort of thing anyway. So it's a good example of where international science can do things that just can't be done at the national level. And I'm going to sort of argue that we need something similar for climate change. Now, you may have your own, if you're concerned or interested in climate change, you may have your own ideas about how a kind of CERN for climate change might function. And indeed, there might be multiple ways in which this concept has some kind of pertinence. But I'm going to talk about a specific aspect which is to do with my own field of climate modelling, where I think to make progress we need to pool resources and combine activity. Okay, so let's move on then. Well, many of us were very in my field. Sorry, is the microphone booming a bit? Is it okay? Many of us in my field were delighted when our colleague Suki Manabe from Princeton won the Nobel Physics Prize in 2021. And he won it really for his groundbreaking work in modelling climate change. And I've just shown you here a figure from one of his seminal papers back in 1975. Do come in. I'm making this point because climate skeptics sometimes say, oh, what have climate models ever predicted, other than the world's going to warm? So what we're looking at here is the response in Manabe's model to a doubling of carbon dioxide in the atmosphere. It's just you run the model with normals, pre-industrial CO2, and then you run the model again with a doubled amount of CO2. And what is shown here on the vertical axis is height. So you're going up, if you look on the right-hand side, 10, 20, 30 kilometers into the atmosphere, up into the atmosphere. And once you get above about 15 kilometers, you go into what's called the stratosphere. It's a different sort of layer of the atmosphere where the ozone is formed. And what we're doing is we're looking at temperature, the difference between the two runs of the model, And the temperatures have been averaged along a line of latitude. So we're looking at the sort of latitudinally average temperature from the North Pole on the left to the equator on the right. So I wanted to point out three things, I suppose. One is that you can see the numbers 1, 2, 3, 3, 2. You can see basically in the lowest 10 kilometers or so of the atmosphere is warming. You can see in particular, if you look near the polar latitudes, near the surface, it's warming particularly. So that was one prediction of Manabe's model, that the Arctic would be a hotspot for climate change. But perhaps the most important thing to take out from this is that in the stratosphere, the air is actually cooling. The air responds by cooling. Now, I'm going to be unashamedly egocentric here and say, if you want to understand that, please read my book, which came out last year, which is I'll talk a bit more about later on. So I'm not going to dwell upon this too much. But the important point to make is that if you had done another, as in fact Manabe did, if you do an experiment where you increase the energy coming from the sun, you increase the radiance hitting the Earth from solar, visible and ultraviolet photons, you don't see this effect of cooling in the stratosphere, warming in the lower atmosphere. It's pretty much warming the whole way up. So this is a very good example of what's called a fingerprint of climate change, of anthropogenic climate change. You look to see, is the near surface warming, is the upper atmosphere cooling? And that's exactly what we see. So that was a really important prediction of Manabe's model, which has been borne out. And it kind of is an indication of why most, if not all, climate scientists are very confident that the warming we're seeing in the last decades is coming from our emissions of carbon dioxide. So it's kind of led to the I don't know, the mantra, if you like, that we know certain things pretty unambiguously. We know that carbon dioxide is a greenhouse gas. We know by burning coal and oil and gas and so on, we're emitting CO2 into the atmosphere. We know we're warming the planet as a result of that. We know from these Manabe results it's not some, as you read about somewhere and you see these odd things on YouTube, it's not because the sun's getting hotter or anything like that. The other thing that Manabe's model would have predicted, because it would have a very simple water cycle in the model, that as the atmosphere warms, more moisture is evaporated from the ocean, so you get a kind of a moister atmosphere. And moisture is a really important quantity in sort of fueling, if you like, storms and systems that bring heavy rainfall. So the latent heat as water vapor condenses into liquid water is a sort of driver. So having this moisture atmosphere leads to more extreme events, which is what we see. So we know that. And we know if we want to reduce the warming and we want to reduce these more extreme weather events, we should reduce our emissions. So that's the kind of standard mantra. Now, this is not what I want to talk about, because this is just sort of settled science. There's no real debate about this. I want to focus on things that we don't know. And one thing, actually, which people may not realize that we don't know, is how bad the warming will get. Will it be a kind of, as some people describe, lukewarm sort of thing of no great significance, or something we can adapt to relatively easily, or would it be existential, where the temperature rise is so great that we start getting heat waves where the humans literally can't survive? And just to make that point, this is a figure from the book. I've taken all of the models that contributed to the last 2 IPCC reports and plotted them as a histogram showing how much, doing pretty much that same experiment that Manabe did, where you double CO2 from pre-industrial to some value that will hit probably towards the end of the century. But how much warming would we expect if we let the system come into an equilibrium with that doubled CO2? And you get this quite diverse range of answers, from 2 degrees up to 6 degrees or more. And so the models are not agreeing on this. why is that? Well, the reason is that the warming we see in the atmosphere is not simply the effect of carbon dioxide, because if it was just carbon dioxide, we know enough about the radiative properties of carbon dioxide molecules to calculate how much warming there would be. It's this sort of knock-on effects, it's the amplifiers that the sort of natural processes that occur in the atmosphere can amplify or not. And the most important one of these that we don't know the answer to are actually clouds. How clouds will respond to our emissions of carbon dioxide. And the reason clouds are complicated is because they do different things depending on how high up the clouds are. So on the left you have what are called cirrus clouds. These are often kind of ice, sort of wispy, icy clouds, which are way up high in the atmosphere, up at sort of 10 kilometers or so. And, you know, gardeners and people like that know that when, you know, if there is a potential for a frost overnight and then a layer of cirrus comes over, quite often that stops the frost from forming at the ground. And in some sense, the cirrus acts a little bit like a greenhouse gas. It's trapping the infrared radiation that leaves the planet, whereas it's relatively transparent to the solar and ultraviolet light. So it's a kind of quasi-greenhouse gas. Whereas if you have the more sort of thicker, what are called stratus clouds, say just only a kilometre or less above the surface, their effect is basically to block sunlight. They just reflect sunlight back to space and end up cooling the surface. So the question about, I mean, one of the complications about clouds is it really depends whether, if clouds increase at a 10 kilometre level, they may end up increasing the effects of carbon dioxide, amplifying the effects of carbon dioxide. If the clouds were to increase at the lower levels, then actually it would have the opposite effect. It would decrease the warming due to the CO2. And now, the reason clouds are kind of uncertain in models for two different reasons. And I think probably the latter is the more important one. But there's one kind of simple effect that, or simple to say at least, which is that as the atmosphere warms, the kind of distribution of droplets and ice crystals and the relative ratio, for example, in these cirrus clouds between ice crystals and like supercooled water droplets will change, and that will affect the radiative properties of these clouds. So there's a certain amount of uncertainty in the what's called cloud microphysics, but the more important uncertainty is the fact that clouds, you know, tend to occur in particular parts of the world, and they're kind of conditioned by the circulation patterns. So in the subtropics, where we have descending air, we tend to get very low cloud amounts. You know, in the equator, where regions where moisture is converging, big circulations converge moisture, monsoons and things, then you get a lot of clouds. So a crucial question for climate change is how is climate change going to affect these circulation patterns? Because that will determine how the global cloud fields will evolve. And that, as I was sort of talking about, is a really difficult problem. That being confident about changes in circulation patterns is difficult. I'll just give you one example. It's kind of, we hear about El Nino in the news all the time. These three cartoons at the top are kind of schematics of the Pacific Ocean, in the sort of equatorial Pacific Ocean, during, well, in the middle is kind of normal situation, the El Nino situation on the left, and the opposite of El Nino called La Nina on the right. And what we're looking at, the red blob is denoting the tropical West Pacific, which is where the sea temperatures are typically warmer than they are anywhere else in the world, and lots of convective thunderstorm type clouds form there. actually the sinking motion, so that induces a sinking motion over the cold eastern Pacific, which actually sets up a stratus-type cloud structure over the eastern Pacific. So actually during normal conditions, you can get a lot of cloud, sort of cloud decks forming, what are called marine stratocumulus decks, in the tropical eastern Pacific. In the El Nino, these thunderstorm clouds kind of move over to the east. This is all part of a kind of complicated, well, sort of semi-complicated dynamical coupling between the atmosphere and the ocean, between there are kind of, I don't want to go through this now because it'll take too much time, but there are modes of variability of the Pacific Ocean which couple with the atmosphere. And an El Nino is where all these thunderstorm clouds move over to the central and eastern Pacific. And the opposite La Nina phase is where actually it gets even colder in the eastern Pacific. So a crucial question about climate change is whether El Nino or La Nina become more likely under climate change. We've actually gone through a period of 3 or 4 years, 3 years or so, of a persistent La Nina, which, for example, has led to the drought and the forest fires that we've seen in California. So again, this is a kind of really order one question. Will La Nina or El Nino become more common under climate change? And for reasons I'll talk about, the models don't agree, so we don't know. Kind of related to that is this question of regional impacts. As I said, Manabe's results are very clear on the global scale. But let's ask a question like this. If you're, the Prime Minister or something of a country and you're trying to set a strategy to adapt your country's economy to climate change, I mean, the basic question is, what actually are you adapting to? Is it things like at the top or things like at the bottom? Well, you might go to the IPCC report for guidance. And here's a figure from the latest assessment report, which shows a kind of an estimate of whether a particular part of the world is getting wetter or drier. This is the seasonal average, December, January, February, or June, July, August. Wetter or drier under climate change. Now, the only thing I want to take away from this is that you can see most of the globe, it doesn't matter which season you look at, most of the globe has got this kind of diagonal kind of cross-hatching across it. And if you look at the table, you'll see that diagonal means no robust significant change, which basically means you're kind of stuffed. If you want to know, is it getting wetter or drier, pretty much the models are not going to tell you. They don't agree. So for most regions, we don't know. Okay, well, you may say, look, who cares? We want to reduce the likelihood of extreme weather. We know we should reduce our emissions. We need to just get on and do it. Who cares? Is that enough? And indeed, there was a kind of a commentary in Scientific American by Naomi Oreskes, which kind of made that point in a sense. Look, okay, we've had all this IPCC stuff. We know climate's changing. Let's kind of just get on and tackle the problem. But I don't think that's the right attitude or the right conclusion to draw. So I want to say why. And I'm going to just take a few examples from different sort of policy aspects of climate change. So mitigation. So we're all building wind farms, which is great, except that we all know that wind farms are at the prey of intermittent weather patterns, anticyclones, where the wind doesn't blow. And there is a kind of a worry here, which is that if you know anything about the dynamics of the atmosphere, you know that the westerly winds that blow are a kind of a consequence of the fact that the pole, the Arctic, is much colder than the equator. So there's a temperature gradient, and the winds are kind of driven by this temperature gradient. So if you're preferentially warming the Arctic, you're reducing this temperature gradient, which means the winds could start reducing. And so you may end up building a load of wind farms, let's say in the North Sea, which turn out to be much less efficient and effective because of persistent low wind speed conditions. The models don't actually agree. Again, unfortunately, you go to the models and say, do they all show the winds are getting weaker? Actually, they don't. And the problem is, the strength of the winds actually is not just a simple function of the surface temperature. It also depends on the upper level temperature gradients, and there's a kind of a battle between the surface, and the models get different things. So all I'm saying is I think this is a serious question. You're building renewable energy in places where currently conditions are very good, but do we know they're going to be good in the future? I mean, it's an important question to answer, I think. Well, I've already shown this diagram. You know, I mean, how are we going to adapt if we don't really know what we're adapting to? Okay, let's move on from that. Geoengineering. So this is an interesting one. It's sometimes mentioned, you know, the plan B, and probably sticking mirrors in space is just too expensive, and that won't happen. Trying to spray clouds is just too, it's a bit wacky. It doesn't really, I don't think it adds up. The only serious way of changing the amount of incoming solar radiation is to spray the stratosphere with what are called sulfate aerosols, or basically sulfuric acid droplets, which create aerosols and reflect sunlight back to space. The problem is you are offsetting a problem in the infrared part of the spectrum. The greenhouse effect is the blocking of infrared light by blocking solar light. So you're not really offsetting one with the other precisely. And the concern is what is going to happen to the hydrological cycle in particular. So to make it more practical, can we be sure we're not going to shut off the monsoons if we do this? Or can we be sure we're not going to shut off the moisture supply to rainforests if we do this? Because if we shut off supply to rainforests, then we suddenly created a carbon sink, you know, of dead trees into the atmosphere. So that's going to be very counterproductive. Now, you may view this as slightly kind of esoteric, but it strikes me, and again, I write about it a bit in my book, that it's not impossible that, you know, countries, for example, if certain countries had persistent drought, and that led to a failure of the wheat harvest and so on, they may start to do this unilaterally. And we need to be ready to be able to say, this is a really dangerous experiment, or actually we think this will do the job until we get our carbon emissions in order. And at the moment we don't know, because these types of questions, again, it's about the regional response to something like sulfate aerosols is too uncertain. Loss and damage. I mean, this is now a big issue. It was a big issue in COP last year in Sharm el-Sheikh. But again, there's a question, if you have an extreme weather event, how much actually was caused by climate change? How much, you know, let's take the flooding in Pakistan last summer. How much of that was caused by climate change? Well, okay, you can look at the models. You can say, I'll look at the models with kind of pre-industrial carbon dioxide and look at the types of look at the types of heavy rainfall events that occurred in that world, and then compare it with the types of heavy rainfall events that occur in a world with double carbon dioxide. The problem is that the models do a poor job at simulating these extreme types of flood events. And there's a very good, I mean, you don't have to take my word for it, there was a report written by the World Weather Attribution, which is kind of seen these days as the world sort of authority on these types of attribution questions. And if you read the headline, it would seem that, yeah, you know, extreme monsoon rainfall was certainly made more likely by climate change. But if you look at the detail of the report, you can see that actually they were not able to answer these questions in any kind of quantitative way. The available state-of-the-art models struggle to simulate these rainfall characteristics, the observed Pakistan rainfall statistics. Those that pass our evaluation test generally show a much smaller change in likelihood and intensity of extreme rainfall than what we found in observations. Conclusion, models are unable to provide a basis to confidently quantify the change in the monsoon seasonal rainfall with climate change up to now. So for all the sort of talk about loss and damage, we're not actually able to do any really meaningful quantification of this. And I think I'm coming to the end of my sort of these points about why this is important and what things that we don't know. A lot of talk these days about tipping points. And the sort of mother of all tipping points that's often raised is what's called the thermohaline circulation. It's sometimes confused with the Gulf Stream, which is a mistake, which I can talk about. But it's basically a big three-dimensional circulation in the oceans, which does play a role in keeping Europe relatively mild compared with, say, parts of Alaska. And it does play a role, for example, it plays a role in setting the sea temperatures, for example, off the coast of Africa, which in turn are important in determining the strength of the African monsoon, and to some extent the Asian monsoons as well. And this is one of the areas where there's a concern that if, for example, if Greenland starts melting, it's injecting a lot of fresh water into the North Atlantic, which is diluting, it's making the water less dense than the salty water it normally is. And that might end up shutting off some of this sort of deep water formation that occurs in the North Atlantic there. Now the thing is, there are simple models of this which actually show this so-called tipping point behavior, where you can sort of dilute the North Atlantic water enough and it just stops, it shuts off. And then you can add salt back and it doesn't switch on again. It's the classic, what they call hysteresis effect. On the other hand, if you look at more complex models, they don't actually show this behavior at all. The thermohaline circulation slows down a little bit with climate change and the freshening of the water, but it doesn't shut off. So we don't know actually which of these is right. And again, it's kind of important because tipping points, passing tipping points, you know, they are irreversible. So if we're confident that we're going to pass a tipping point, it puts a lot of pressure, I think, on the politicians to come up with immediate answers. Okay, I just want to say a few words about the origin of these uncertainties and then how we can reduce them. The most important point to make is that models are not just people's kind of intuition about how the laws of weather and climate work. They're based on the laws of physics. So we've got Newton's laws of motion, we've got Max Planck's law for how photons are absorbed by different molecules in the atmosphere and then re-emitted as infrared radiation. So we use some of the laws of quantum mechanics. And the guy on the right is Rudolf Clausius, who was one of the pioneers of the laws of thermodynamics. That's his entropic law. So we use the laws of thermodynamics, quantum mechanics, and classical mechanics in formulating a climate model. This is the form of the Newton's laws that's used in the model, and it's called the Navier-Stokes equations. They're kind of, well, they might look intimidating if you're not a mathematician, but they're kind of beautiful laws because with a relatively small number of symbols, you can describe pretty much every dynamical interaction that goes on in the atmosphere and ocean. And this equation describes the turbulence of a fluid. That's a liquid, turbulent liquid. The atmosphere is a turbulent, sort of gaseous fluid. And if you were a mathematician, you would know in some sense that these equations have a very important symmetry that gives rise to this notion of turbulence, which is that you can scale, if you have a solution of the equations, you can kind of scale it in a certain way, like you zoom in and the solution holds at a smaller scale. So it's called a scaling symmetry. And it's basically consistent with the fact that, you know, if you were to zoom into that turbulent fluid, it would kind of look the same to first order as looking at it on the larger scale. This is important, which I'll come to, because what we do in a climate model, because we have to solve these equations, you can't solve them with a pencil and paper, you need computers, you need big computers. And what you do is you sort of what is called project the equations onto a grid. So here's the world, the atmosphere and the oceans, and you've got this kind of grid. And the idea is that within a grid box, you're kind of assuming the atmosphere is completely uniform and homogeneous. And of course, that's not the case. The atmosphere has turbulence all the way down to individual molecules. But, you know, that's the approximation you have to make to solve the equations on the computer. And with current computers, most climate models that go into IPCC, these grid boxes have a horizontal dimension of about 100 kilometers, 100 in one direction, 100 in the other direction, and maybe going upwards a couple of kilometers. Because the atmosphere is very thin compared to, what latitude was it? Now, when you truncate these equations to 100 kilometers, you know there are lots of processes, such as cloud processes, which you're not resolving. The clouds occur on scales much small, individual clouds are occurring on scales much smaller than 100 kilometers. So that's where you start to make approximations. You have people develop very simplified formulae which kind of give you what they would call a bulk representation of clouds or flow over small mountains or turbulence or something within these grid boxes. And these are called parameterizations. And in a sense, this is where the inaccuracy starts to come in. It's not at the level of the equations. We think the equations are pretty damn accurate for all intents and purposes, but it's this parameterization that's the problem. So, for example, I just mentioned three processes. So thunderstorm clouds, you can't resolve them in a climate model. You have to parameterize them. This is flow over, I mean, I did a lot of work on this many years ago, flow over mountains, which, you know, if the mountain if the air is moist enough, you can see these clouds forming, which are indications of what are called gravity waves. And these gravity waves can propagate vertically, and as they propagate into a less and less dense atmosphere, their amplitude gets bigger and bigger, and eventually they break like waves on a beach break. And the net effect of that is that they actually transfer momentum from the bottom of the Earth, from the surface of the Earth, right up into the upper atmosphere. So if you want to get the structure of the winds right throughout the depth of the atmosphere, parameterizing these what are called orographic gravity waves are pretty important things to do. But they're parameterizations. You can't resolve them. The wavelength of one of these waves is a few, maybe 10 kilometers or so. And then if you look in the oceans, you see, for example, these little eddies and things, which oceanographers who do studies of these things show are important for conditioning the large-scale ocean circulations. So again, you have to parameterize these small-scale whirls and eddies that are in the ocean. This is looking at the Gulf Stream as it separates from the US. Now, just a bit of, I don't want to go into too much theory, but the kind of thinking behind a parameterization is very much like people who studied what are called statistical mechanics many years ago, where you can derive the notion of a viscosity of a fluid by thinking about the fact that the fluid is actually made of lots of little atoms which are banging into each other. And providing you don't look at the individual atoms, you just step back and look at things on a large enough scale, you can represent the bulk effect of all these molecules and atoms banging into each other by a kind of what's called a viscosity formula. And this is the philosophy that people have used in developing parameterization. So the idea is you think within one of your 100-kilometer grid boxes there may be loads and loads and loads of little clouds, and can we come up with a formula not for any individual cloud but for the sort of bulk effect of the clouds. The problem is that because of this scaling symmetry of the Navier-Stokes equations, this is actually not how the world works. When you actually look at real satellite photos and things, you don't see lots and lots of, well, very rarely, you might occasionally, but most of the time you don't see lots and lots of little clouds. You see a whole spectrum of clouds, some quite big and indeed comparable with the grid scale, and some not so big and some small. This is what we call a power law for those who know about these things. So this actually makes the whole concept of parameterization a little bit shaky, I would say. And a result of that is that climate models don't actually they don't simulate the real world perfectly. There are biases and systematic errors in models. This is a paper I wrote with the director of the Max Planck Institute for the proceedings of the US National Academy, where we compare, on the left-hand side is the sort of systematic error of climate models against observations. And on the right-hand side, this is for rainfall, on the right-hand side is the climate change signal for a sort of doubling of CO2 that the models simulate for the same precipitation rainfall field. And what you can see is that the systematic errors are, if anything, actually slightly bigger than the signal. And if you know anything about a nonlinear system, that's not a good place to be, and there's potential for unreliable predictions because of that. Okay, so the question is, what would be needed to represent these processes properly, not using parameterizations, but with the laws of physics? Well, in a sense, it's very simple. You just increase your model resolution or decrease your grid box size to, say, around 1 kilometre. Problem is that's easier said than done. Climate institutes don't have big computers typically. I mean, they have quite big, but they typically don't have the top range of computers, and they can't do this. On the other hand, now if I can get this to work, we can start to look at what a 1 kilometre climate model would look like. So this is a 1 kilometre, so we can write the code and we can run it for a few days. This was actually done by my colleague from Max Planck, starting, this is on the left, it's the iconic photograph taken by the Apollo mission in 1972. And they've used that as an initial condition and then run their simulated 1 kilometre model. But we're not running it over decades, we're running it just over a few days. Because there just isn't the computer resource to do it. So these are clouds, they're quite realistic looking cloud fields. This is the ocean temperature over the Indian Ocean. And then I think we're going to look at, you can see some of these eddies in the ocean starting to get very well resolved. Again, cloud pictures, and these are wind speeds. You can see these fronts, well, you just see the front in the kind of discontinuity in the wind speed. Anyway, so I'm just saying a 1 kilometre model can be run, but to realistically envisage kilometre scale climate simulations, we're going to need this new generation of computers called exascale. This is 10 to the 18 floating point operations per second. So whatever that is, million per second. And in fact, in the US, the Oak Ridge National Lab, the Department of Energy's National Lab, has one of the first of these. So these exist now, but you know, this one and the others that exist are, probably some of them are used for national security and we just don't know about them, but the ones that are known about are used across a range of applications, not just climate. And if we're going to seriously envisage getting to K-scale, what I call K-scale, kilometre scale, we're going to need dedicated exascale computers. So I've been sort of banging on about this. So this is my CERN for climate change, a dedicated facility for dedicated exascale facility, pooling human, computational, financial resources. This is something I wrote well over a decade ago. Actually, more recently, last year, some colleagues, Julia Slingo, the lead author, was the chief scientist at the Met Office. And these are another, I mean, Thomas Stocker was the head of the IPCC Working Group 1. He was the Working Group 1 chair for many years. Bjorn Stevens is the director of the Max Planck Institute. So these are quite big names in our field. As I'll say, I don't envisage this as necessarily just being one institute, but maybe a global network of institutes. Importantly, it would be a meeting ground between scientists from the global north and global south, and it would also be a meeting ground between climate, which is like what I've talked about almost entirely in this talk, and the sort of impact communities that feed off that data, the economists who are trying to measure the economic impacts of climate change, the hydrologists looking at whether particular river basins, when they're going to flood and how often and so on. The agronomists are trying to decide what's going to be the ideal types of crops to grow in particular places. People looking at disease malaria and other types of diseases that might have that do have a weather component to them. So certainly impact science, which I haven't really given a great deal of attention to, is something which will be very important. And this is a kind of fairly trivial point to make, but even something simple like getting the topography right in a model, rather than having to average it over 100 kilometers, will be pretty important if you're trying to determine the watershed for a river, where the rain is going to drain into the river. With a 100 kilometer model, it's very difficult to say anything very much. Now, I was quite, I've sort of got just a few more slides and then I'll finish. I was quite pleased to read a very recent report by Paul Nurse, who, he was the president of the Royal Society, he's now the director of the Crick Institute. But he wrote a kind of report on, it's got a bit of a mouthful of the title, but it's basically about infrastructure for science. And he says there are research areas of global strategic importance where new multinationally funded institutes or international research infrastructures could be contemplated. An obvious example being an Institute of Climate Change built on the EMBL model. Now, I don't know if people know what EMBL stands for, EMBL, European Molecular Biology Lab. I've got a couple of slides on that in a second. Such institutes are powerful tools for multinational collaboration and bring great benefit, not only internationally, but also for the host nation. So I think that was a really helpful couple of sentences to have written. So I've been using that when I'm in discussion with UK government officials. Just to say a couple of things about EMBL. It's been running quite a few years now. European Molecular Biology Lab has, like CERN actually, it has partners from all over the world, not just from Europe. And it's been extremely successful in many different areas of molecular biology. But one important thing which I was kind of pleased to learn is that although we talk about EMBL as if it was one place, it's actually not one place. It's a kind of network of labs that do different aspects and of the problem. And I kind of see this CERN for climate change in a similar way. But now not just thinking about Europe, but maybe a set of centres, one in Europe, one in China, one in India, one in Japan, one in Korea, maybe South America, but highly interconnected and highly collaborative and so on. Now, one really important thing, and I discussed this with Paul Nurse just to make sure I had it right, but EMBL works very harmoniously with National Institute. They both kind of feed off each other. Tension, as I understand it, between them. And I really would hope the same for the CERN for climate change. We would be building on expertise developed at national institutes. I say this because sometimes people get kind of nervous that this will take over somehow and make the national institute redundant. And I absolutely don't think that would be the case at all. So where do we go from here? We're having quite a big, big as not as in lots of people, but important, I hope, conference/workshop in Berlin in July to really kind of flesh out the details of this. We're going to develop a series of white papers. We set out the science, the impact science, and importantly the finance, how much this will cost. We have some pretty kind of big names coming to give lead talks. Jensen Huang is the founder and CEO of NVIDIA, who's extremely enthusiastic about this program. We've got the Director General of CERN coming. We've got Franz Timmermans, who's basically the one below Ursula von der Leyen in the EU. We've got the Director General of the UN World Meteorological Organization, who's also very, very enthusiastic. And what we're hoping to do is that this will kind of go on through to the COP28 meeting, which is in Dubai this year, and we're hoping that this will be formally endorsed and maybe even financed. at COP28, but we have to keep our fingers crossed about that. If I had time, I would have talked about, because I don't want to give you the impression that we have been kind of the world of artificial intelligence, which of course has come on enormously in the last few years, has kind of passed us by. And there are lots of ways in which AI can be used to speed up and make more efficient the computations that we will be doing as part of this K-scale modelling. I think I'm not going to go into this because it's a little bit perhaps late in the talk and people may not be interested. But there are, unlike quantum computing, where I don't think there's much application, I'm afraid, as yet, AI has a lot of potential for improving, particularly things, as I say, things like computational efficiency, which are going to be crucial for this project. And that's my last slide. So, as I say, a lot of this I have talked about, and Moritz kindly printed off some flyers, and I think OUP are giving some discount if you want to buy the book, but it's kind of about the science of uncertainty, and I cover a number of different areas, and climate change is one of them, economics, COVID and stuff, as well as quantum uncertainty. But a lot of the figures I've used are from the book, so if you're interested, please do read. So yeah, I'm trying to give you a kind of I kind of sense the media, the climate-friendly media are reluctant, let's say, to talk about the fact there are uncertainties in our predictive capabilities. So there's some of what I've said today I don't know if it'll shock you, but you may be surprised, actually. There's a lot of stuff we don't know yet about climate change that I, for one, would love to know. I don't think my message undermines the basic message that we need to take action now, because if I went back to the second slide, you could see that there is clearly a substantial probability that we could hit temperatures of 4, 5, 6 degrees. Now, these would unquestionably be catastrophic and indeed existential for large parts of humanity who were living in the subtropics and tropics. So there's no question uncertainty doesn't in any way compromise the basic message that we need to take action if we want to reduce these risks, as I think any kind of sensible person would probably think. I certainly argue that in my book. I go through quite a lot of cost-loss analysis, trying to argue why we can make decisions under uncertainty. We do make decisions under uncertainty all the time. So I hope I'm not compromising that basic message. But on the other hand, it is important that we understand better, particularly at the regional scale, what's happening. And the frustrating thing is it's not a matter of better science. We don't need to discover the next thing after the standard model, because we know our equations. We just need the technology to solve them accurately. And in the big scheme of things, because we are talking sort of around a couple of $100 million a year for one of these institutes, it's not actually that much money. I mean, compared to a satellite mission or any other thing, it's not a lot of money. So it's just a question of persuading the powers that be. And I'm keeping my fingers crossed. As I say, COP28 might be a turning point. So let's hope. Thank you.